Hello, and in this video we're going to talk about a probability rule called Bayes' rule. So this rule is going to allow us to sort of work backwards in terms of logic for some of the probability problems that we may be exposed to. So let us briefly review just those rules that we've discussed so far for probability. So the first one was the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A intersection B. And we found that if these events are mutually exclusive, then we get that this is just equal to the probability of A plus the probability of B. So this was what we call the sum rule. And the second big rule that we pretty much discussed was, well, if A and B depend on one another, then we have that the probability of A given B is equal to the probability of A intersection B divided by the probability of B. And if A and B are independent, then we get that the probability of A given B is just the probability of A, or more so, the probability of A and B is equal to the probability of A times the probability of B. And that's what we call the product rule. So these are two useful formulas that are commonly seen, and you can combine these formulas in any way you desire. So what this rule is going to allow us to do is sort of work backwards in terms of logic. So let us take, for example, the rain and umbrella example. So let R be the event of it raining, so raining, and let U be the event of buying an umbrella, so buying an umbrella. So what is U given R? What is this event? So this is the probability of buying an umbrella, assuming that it is raining. So it's already raining. What is the probability of buying an umbrella? So buying an umbrella is the event of interest, or the event that it's about to happen. So that's sometimes, not what we're interested in. So this probably would be an event that a business would be interested in, right? Because it's raining outside, so we're hoping that people come into our store to buy umbrellas, right? Now let's switch the perspectives around. Let us assume the event R given U. So that means what? It's already, or we already bought an umbrella. An umbrella is bought. So this is pretty much from the consumer perspective. So we go to a store, it's not raining outside, but we buy an umbrella because we think it's going to rain. So pretty much, what is the likelihood of it raining, assuming that we've already bought an umbrella, right? So therefore, the event of interest here is raining outside. So this is the event of interest, or the event that it's about or not about to happen. All right, so let's assign some numbers here. So let us assume that the probability of it raining is equal to 7 divided by 15. Let us also assume that the probability of a person coming into a store and buying an umbrella is going to be 7 out of 10. And let us also assume that the probability of buying an umbrella, assuming that it is raining, is equal to 9 divided by 11. And usually businesses can usually generate these probabilities. These likelihoods are usually generated by meteorologists or businessmen, or a combination of both. So let us determine what is the probability of it raining, assuming that we have already bought an umbrella. So how can we find this actually? So, well, we already know that this is equal to the probability of R and U divided by the probability of U. But we do not know the likelihood of it raining and buying an umbrella. So what can we do here? So what we can do is multiply top and bottom of this expression by the probability of R. So let's do some work here. And from here, let us rearrange. I'm going to rewrite this in a little different way. I'm going to call this the probability of U and R, because they are actually the same. divided by, and I'm going to take this probability of R and put it there. So probability of R times, and I have that probability of R there, and I have the probability of U still on the bottom. Now, what exactly is this? Well, that's the conditional probability of U, assuming R has already occurred, by definition. And then we have this probability of R on top. And then we have the probability of U on bottom. And we already know what these three components are, so we can just substitute them in. So what do we have here? So the probability of U given R is assumed to be 9 divided by 11. The probability of R is equal to 7 divided by 15. The probability of U is assumed to be 7 over 10. And we can work around some fraction stuff. So we have 9 on top, we have 7 on top, and we're going to have 10 on top once we keep change flip. On the bottom we have 11, we have 15, and we're going to have 7 there. So what do we have? Well, these 7s can eliminate one another. Nothing else simply cancels, so I'm just going to multiply this out. So that's going to come out to 630 divided by 1155, if you keep the 7s there. So let's just keep the 7s. So that's going to come out to 0.54 repeated. So there's about a 54% chance that it actually does rain, assuming that you already have bought an umbrella. So pretty much a property that I've pretty much derived here in the process is the following. So let us assume we have the probability of A given B. This is the same as the probability of B given A multiplied by the probability of A, all divided by the probability of B. And just in case you haven't seen pretty much the connection here, B is always serving as the sample space, so that's always going to be in the bottom of this expression. So this is what we call Bayes' rule. Bayes' rule. All right, so let's do another example of Bayes' rule to sort of demonstrate this idea. So example 2. Suppose we roll 2 10-sided die. So roll 2 10-sided die. So when I say a 10-sided die, that means my sample space is going to have all the values from 1, 1, 1, 2, all the way down to 1, 10, all the way down to 10, 1, and all the way out to 10, 10. So if that is the case, then that means the size of my sample space is going to be 10 squared, or 100. And let's consider a couple events here. Let us consider the event A of rolling a sum that is equal to 15. So how can I get a sum of 15 here? So I can get a sum of 15 by either getting a 5 and a 10, a 6 and a 9, a 7 and an 8, 8 out of 7, 9 out of 6, or 10 and a 5. So if that is true, then that means the size of my event A is going to be equal to 6. Let's consider my event B. Let B be equal to the event that at least one die, or dice, is a 6. So at least one die is a 6. So that means I can have 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, all the way down to 6, 10. Or I could have the event 1, 6, 2, 6, 3, 6, 4, 6, 5, 6. I'm not going to include that one because that event has already occurred, all the way out to 10, 6. So that means I have what? So this is pretty much like 10 times 2 minus 1, so that's going to be equal to 19. All right, so what do I have here? So that means the probability of A, assuming B has already occurred. Well, what is this? This is the probability of A and B all over the probability of B. So how many people are in both A and B? So let's look at our sets here. So A and B. So who is in both? So that means the sum has to be equal to 15, and at least one must be equal to a 6. So that means 6, 9 must be there, 9, 6 must be there. So there's going to be only 2 of them. So the probability of getting one of those is going to be equal to 2 out of 100. And the probability B is going to be equal to 19 out of 100. So that probability is going to be equal to 2 divided by 19. So that's the probability of A, assuming that B has already occurred. So let us consider the main problem of interest here. What is the probability of B given A? And sometimes you may want to find one before the other because it might be easier to find that. So what are we assuming here? So we're assuming that our sum is equal to 15. Remember, this is the smaller set of interest, right? So that's probably why you would want to find this first, or maybe second, depending on the scenario here. So let's assume we're not really interested in those things. But in general, this is going to be equal to the probability of B times the probability of A given B all over the probability of A. So I'm just going to substitute all these things in here. So the probability of B is going to be 19 over 100. The probability of A given B is given to be 2 divided by 19. The probability of A is going to be 6 out of 100. And let's see what we have here. So these 19s are going to eliminate. And these 2's are going to eliminate with the 6, leaving us with 3. And then these 100s are going to cancel as well. So we're just left with what? This is just equal to 1 over 3. So that means the probability of getting a value that is at least 1/6, assuming that we have already got a sum of 15, is equal to a third. That means that's going to happen 33% of the time. So let us recall what Bayes' rule says, and this is useful if you want to sort of work backwards from the logic that's presented. So let us assume we want the probability of A given B. So you will only use this rule if the probability of B given A is easier to get. If that is true, then you can just say, okay, this is equal to the probability of B given A times the probability of A over the probability of B. And you will only really use this if this is easier to get than that. If you can just get probability of A given B directly, then you probably will. But there are some instances where you won't. And that's what Bayes' rule says.